Okay, folks. So in the last problem, we looked at how the area of a square was changing as the sides were increasing. So the sides were increasing. We asked the question, how fast is the area of the square changing as those sides are changing? We're going to do the same thing now. A very similar problem. In this case, we have a cylindrical tank. It has a radius of 5 meters, and it is being filled with water at a rate of 3 meters cubed per minute. Okay. So in the last example, I emphasized that when you see this word rate, that's a rate of change. Well, it's a rate of change of what? It says for the cylindrical tank with a radius of 5 meters, it's being filled with water at a rate of 3 meters cubed per minute. And in fact, if you're confused, look at the units. These are the units here are meters cubed. So this is a statement about what? What sort of quantity? Think about that for a second. So it's a rate of change in volume. So this is dV dt. Okay? So we're told that the change in volume of the water is 3 meters cubed. We're asked the question, how fast is the height of the water increasing in this problem? Okay, so for all of these, I didn't list it in one of the steps, but it might be helpful to draw a picture. So here we've got a cylindrical tank, and in this cylindrical tank we have some water at a level, okay? And the height of the water is increasing. So if we call this distance right here h is going up, right? Well, we want to know how quickly is the height increasing. What do? We do know that water is entering here at a rate of 3 meters cubed per minute. So how quickly is that height changing? So if we were to jump back and look at the steps from the previous section, okay, so this is getting a little messy. The first thing we want to do is we find a formula that relates the quantities. We're finding a formula that relates the quantities that we're working with. Okay. So what's a formula that will relate the volume of water in this tank to its height? I'll let you pause the video, think about that for a moment. When you think you've got an answer, go ahead and resume. So what's going to relate all of this together? Well, I'm pulling back on my geometry knowledge, and I'm remembering that the volume of a cylinder, boy, don't judge me on my spelling, folks. The volume of a cylinder includes both, it calculates the volume and it includes the height of that cylinder. So if you remember this, the volume of a cylinder is pi r squared h. Okay? To be honest, I feel like that's a formula that everyone should have memorized. It's easy to memorize if you think about it as having 3 dimensions. So there's 3 dimensions to this cylindrical tube of water, okay? And the lower dimension, the first 2 dimensions, could be thought of as just being a circle, right? So how do I find the area of a circle? That's the area of a circle, and then I cross it with the 3rd dimension, the height. So I do think that's a formula. I would hold you responsible for knowing the volume of a cylinder and would not necessarily give that to you if I wanted you to know it. Okay. So now that we've got a formula relating these, we're going to implicitly differentiate both sides. Do you remember what sorry, this sounds a little pedantic. Do you remember what variable we should use to differentiate with respect to? Pause the video and think about it. You're right, it's time. So we're going to differentiate both sides of this equation with respect to time. And that is the case for most of these related rate problems. How come? Because rate is generally as a unit of measurement per unit time. Okay, so that's why we're differentiating with respect to the variable t. Okay, so this gives us dv dt, or you could write v prime, nothing wrong with that, is equal to, okay. Now this next question is kind of an interesting one. I'm going to take maybe the longer route because I want to talk about it. I have 2 unknown variables here, right? Radius and height. Okay, so when I go to take the derivative, I'm going to have to use the product rule. Some of you might be objecting to that, and you're not wrong in objecting to it. But I'd like to go ahead and use the product rule anyway, and then we'll talk about what happens. So I'll go ahead and treat pi r squared as the first, and we'll treat h as the second. So here we go. We've got the first times the derivative of the second. Well, the derivative of the second would just be dh dt. The derivative of h with respect to t is just the derivative of h. Okay? So that's my product rule. Plus the second, which was h, times the derivative of the first. Times, what's the derivative of pi r squared? It would be 2 pi r times dr dt. So this one was a little more complicated than the last one because I treated both both the variables r and h here. I treated both of those as variables that are related to time. Because of that, when I went to take the derivative of this right-hand side, I had to use the product rule because they're being multiplied together. Okay. So again, this was the first here, then the second. Botched that up. The second, and then plus the second, and then all of this here is the first. Okay. So pause the video if you have any questions and work slowly through that. Make sure that makes sense. Okay. So let's continue. So of all of these unknown quantities up here, of all these quantities up here, which one are we trying to find? Okay, let me just recopy this because it got a little messy. We have dv dt equals pi r squared dh dt plus h times 2 pi r dr dt. So let's go look at our question one more time. Okay. And we are asked to find what? We're asked to find how fast the height of the water is changing. So what are we being asked to find here? We want to find what? What quantity? What would we call that? Think about that for a second. Pause the video before going forward. Yes, we want to find dh dt. Okay? So that's what we're after. Okay? Now, let's start filling in what we do know. Okay? Do we know what dv dt is? The change in volume with respect to time. Well, yes. If you go back to the original question, we were told that the dv dt is a fixed 3 meters cubed. Okay? So this is fixed at 3 pi. Do we know what the radius is at this point in time? Yes, we do. We were told the radius was 5 times dh dt. That's what we're trying to find. Okay. Plus, do we currently know what the height of this tank is? No, so we're maybe in trouble here. Let's find out. Times 2 pi and then times r. Well, r we know is 5 in this problem. And then here's where I've sort of been misleading you. Let's talk about dr dt for just a second. Interpret that for just a second. This says, how does the radius change with respect to time? Think about that and decide what the answer is. Pause the video. So how does the radius change in this problem with respect to time? Well, it doesn't. Water is filling into this cylinder and the walls of the cylinder are fixed, so the radius for this cylindrical column of water is not changing. So what does that mean that dr dt is? That means that dr dt is 0. So even though we didn't know what this h was here, this whole expression vanishes. So we are left with 3 is equal to 25 pi dh dt, and I'll just go ahead and emphasize that by putting plus 0 here. So now we can solve this equation for the unknown rate dh dt, and we get that dh dt is equal to 3 over 25 pi. Okay? That's how quickly this water is changing. The height of this water is changing with respect to time.